Hi, we've finished Module 1 and are starting the second module. We're still going to consider problems from the branch of mathematics called Operations Research, which deals with optimization, trying to do the best you can under given conditions. So still talking about making the cheapest product or the fastest car or the highest quality that you can get for a given set of resources and so on. But the mathematics behind the techniques will change rather dramatically here. Instead of dealing with graphs in the sense of vertices and edges and tours and spanning trees and so on, this is going to be a very algebraic based topic. I don't know where you are in terms of algebra background. On the information form, some of you indicated that algebra was one of the areas of math you felt more comfortable with, and others said otherwise. What I would like to do in this short video is go through some of the background algebraic techniques that I hope you've had before, so this hopefully will be review. If you feel uncomfortable with those techniques and would like more review, in the folder where you found this video there is also a PDF handout, a review handout, that contains some pages from a algebra textbook, and contains a number of worked out examples plus exercises with solutions. So if you feel like you need more practice after watching this video, feel free to go there and look at the examples and work some of them, work some practice problems until you're comfortable doing the kinds of techniques and situations that I'm going to do in this video. If you feel like you want to do that, I would do so very quickly because we're going to be using these techniques to do applied problems very soon, and so the algebra background will be assumed, and then we'll be able to focus on the new operations research. Linear programming is the specific technique we'll look at. Let's first review a little bit about graphing. Here's an equation, 2x plus 3y equals 12. And I hope you remember from an algebra class that the graph of this equation is going to be a line because both variables occur to the first power. There's no multiplication or division involved here. It's a number times x plus a number times y equals number. Those types of equations have linear graphs, graphs which are a line. And in an algebra class, you've probably talked about things like slope-intercept form and standard form, which this is, as means of generating a particular graph. I'd like to do something a little different here, and I think you might find it helpful for the types of lines that we're going to be graphing. Let's actually find not just the y-intercept of this equation, but the x-intercept as well. And so first let's work on the x-intercept. And what is it about an x-intercept? This is the place where y equals 0. An x-intercept is where the graph crosses the x-axis, and that is the one and only place on a line where the y-coordinate is going to be equal to 0. Well, okay, if the equation is 2x plus 3y equals 12 and y equals 0, then we're talking about the equation 2x plus 3 times 0 equals 12. But of course 3 times 0 is 0, and so this is going to say that 2x equals 12, or in other words that x equals 6, or in other words that the x-intercept is 6, 0. X is 6 and y is 0. And so here is a point on the graph, a special point on the graph. Let's also find the y-intercept. The thing about the y-intercept is the graph is crossing the y-axis there, and so x equals 0. And then the equation becomes 2 times 0 plus 3 times y equals 12, or in other words, 3y equals 12, or in other words, y equals 4. And then the y-coordinate of 4 leads to the intercept itself being the point 0, 4. So this line goes through 6, 0, and also through the point 0, 4. and 2 points determine a line, and so we're ready to draw it. In this particular unit, I'm going to emphasize that we put the coordinate axis on our graph in such a way that we're able to display as much of the interesting part of the graph as possible. And in many of the problems, x and y are going to stand for counts of items or weights, and so for physical problems, those have to be positive numbers. So quite often, not always, but quite often, we're going to be interested in the situation where x and y are positive. For that reason, I'm going to put the coordinate axes here. So remember, x on the horizontal axis, y on the vertical axis. And then I'll be able to draw the graph in a region where both x and y are positive. Okay, let's put a scale on the graph. I see that for x values, I need to go out as large as 6 if I'm going to show the crossing point, the x-intercept. There's no reason why we have to go 1 unit per 1 square per unit. In fact, in most situations, it makes more sense to choose another scale, again, so that you can use as much of the axis as you can. In this case, if I need to go out to 6, how about we choose 2 squares to be 1 unit. And so 1, 2, 3, 4, 5, and 6. And now we know that 6, 0 is a point on the graph, specifically the x-intercept. Also, 0, 4 is the y-intercept. So if I come over here again, I think it makes sense to choose about 2 squares for 1 unit. So like this. And by the way, it's not necessary to use the same scale, 2 squares per unit, on both the x and the y-axis. Choose them independently, whatever makes sense for each axis. In this case, 2 squares per unit seems to make sense for both scales. And then 0, 4 is another point on the line. And if I know 2 points on the line, I can draw the line. So connecting these, here's a rough graph of the line that we're trying to draw. And I'll label it with its equation. Okay. This is called intercept-intercept form in some sense. You find both intercepts and then draw the line that connects them. You could use slope-intercept form as well. I think that this method is actually often easier than slope-intercept form. Let's look at second type of problem. Solve the system 3x minus 4y equals 1 and 2x plus 3y equals 12. Okay, that means to find all of the coordinate pairs x, y that satisfy both of these two equations. And there are several ways of doing that. One is graphically, and so let's look at that, and then we'll also do the problem another way. First of all, let's find the intercepts of both of these lines. The second equation is the one we were working with before, and so we already know that its intercepts are 6, 0 for the x-intercept and 0, 4 for the y-intercept. For the first equation, if you think about it, let's go for the x-intercept first. Now set y equal to 0, and let's not bother to write the 4 times 0 now. It just means that the second term is going to drop out. And so 3x equals 1 means that x equals 1/3, and so the x-intercept is 1/3, 0. And to find the y-intercept, set x equal to 0, and you would get minus 4y equals 1, which tells us that y equals minus 1/4. So the y-intercept is 0, negative 1/4. Okay, let's draw these graphs. I'll put coordinate axes about here and here. Doesn't matter exactly. And then intercepts. So maybe I'll go 1 square per unit this time. And so 1, 2, 3, 4, 5, and 6. No particular reason for doing that. I could have used the same scale as before, except I have another line to graph, so I should choose a scale that allows me to represent both lines reasonably well. And 1, 2, 3, 4, if I go 4 squares per unit. So the second line actually that we already did in the previous exercise goes through these 2 points. That's the line 2x plus 3y equals 12. All right, the other one has intercepts very close to the origin. Minus 1/3, 0. So on this scale, that's right in here. And 0 minus 1/4. So that's very close to the origin indeed. If I had it to do over again, I might have expanded my scale a little bit. So here are the 2 intercepts, and those 2 points determine a line, the other line. So it's like this. This is the line 3x minus 4y equal 1. And you probably remember then what we're looking for is the set of points that satisfy both equations. Graphically, that means the set of points that lie on both lines. And so it's right around in here somewhere. Now, maybe it looks like you can tell where this is at, approximately 3, 2. In general, though, graphical methods are only approximations, and sometimes we want an exact answer. So this may or may not be 3, 2. In particular, I'm not very comfortable with the accuracy of drawing this green line because the intercepts were so close to the origin, and maybe I was off a little bit. So this was a graphical solution, or a graphical approximation would be a better way to put it. Let's actually find an exact answer algebraically with something called the elimination method. Here we have 2 equations in 2 variables. We're going to eliminate one of the variables to get down to 1 equation in 1 variable which we can solve. So let me just go ahead and recopy the equations. 3x minus 4y equal 1 and 2x plus 3y equal 12. Now I can scoot that up. For reference, let's call this equation number 1 and equation number 2. And now I want to get one of the variables to drop out by adding or subtracting one of the equations from the other. As it stands, though, if I add or subtract the equations, neither of the variables are going to drop out, and so you may remember multiplying each of the equations by a constant in order to get one of the variables to have coefficients that are the same, and then when you subtract, they do drop out. So in fact, let's get x to drop out. It doesn't matter which you choose. I'm going to try and get x to drop out, and I'll look at the coefficients on the x, 3 and 2, and say the least common multiple of 2 and 3 is 6. So I'm going to try to get 6's now in front of the x. And to do that, let's multiply equation 1 by the constant 2 and equation 2 by the constant 3. Okay, So let's do that. I'm going to equation 1. I'm multiplying every term through by the constant 2. 3x times 2 is 6x. Minus 4y times 2 is minus 8y. Equals 1 times 2 is 2. And then in equation 2, I'm going to multiply through by 3. So 2x times 3 is 6x. 3y times 3 is 9y. And 12 times 3 is 36. Let's call this equation 3 and this equation 4. And we can think of these as being grouped together like this. Now, the x coefficients are alike, and so let's subtract equation 4 from equation 3. So I'm taking this equation 3, subtracting off equation 4 term by term, and generating a new equation. And the reason that's helpful is 6x minus 6x is 0x, or in other words, it's just gone. Minus 8y minus positive 9y is minus 17y. And 2 minus 36 is minus 34. Negative 34. This is an equation in one unknown y. To solve for it, I would divide both sides by negative 17 and get y equals negative 34 divided by negative 17 is positive 2. And then if you remember the way you finish this off, now that you know the numerical value of one of the variables, is to plug it back into one of the equations and solve for the other variable. It doesn't matter which equation you choose as long as it has both x and y. I'll plug or substitute y equals 2 into, let's go back to equation 1. And then I get 3x minus 4 times 2 equals 1. Okay, let's solve for x. Here's an 8. Let's move it to the right-hand side. So 3x equals 1 plus 8 is 9, and then x equals 3. And so the solution is x equals 3, and y equals 2. That's an exact answer. And it's the only solution. This problem has a unique or just one solution. So it looks like our graphical method in this case was pretty accurate. That might have been what we guessed. There's no reason though really that the coordinates of the solution have to be integers. So ahead of time we didn't know that this might not have been 3.1 and 1.97 or something like that. So the algebraic method, the elimination method, is preferred. Okay, you should be able to do that type of problem. Here's another thing that we'll have to do. Sketch the solution of the inequality x minus 3y is less than or equal to 4. Okay, you may remember the difference in the solution set of an equality and an inequality. If this were an equal sign, we know that the graph would be a line, and in fact that line is an important line. So let's first consider the related problem, x minus 3y equals 4. And if I apply the intercept method, and look for the x-intercept and the y-intercept. For the x-intercept, y is 0. So if I come back here and set y equal to 0, I see that x is 4. And for the y-intercept, I set x equal to 0. If I come back to the equation and set x equal to 0, I see that y is, okay, take 4 divided by the negative 3 minus 4/3. And so if I graph this, I can put the y-axis here and the x-axis in here somewhere. Why am I choosing that? Well, I know that I want to be able to graph at least the point 4, 0 and the point 0, negative 4/3. So I'd like to save some space out here to the right so I can get out to positive x values, and also to save some space down here so I can get down to negative y values. And now how about 2 squares per unit? So here's 2 and 4. And then on the y-axis, I don't need to go as far, so maybe 4 squares per unit. So here's negative 1, negative 2, and so on. Different scales on the x and y axes. That's fine. Okay, if I graph the intercepts for 0 is here, and 0, negative 4/3. So that's negative 1 1/3, and that would be about here. And so the line that we're looking for is this one. This is x minus 3y equals 4. All right, I didn't want the graph of a line, I wanted the graph of an inequality. Perhaps you remember shading regions. It turns out that the solution to the inequality is either going to be all of the points up above and to the left of this line, or all of the points to the right and down below this line. So now all we have to do is find out which of those two cases is correct. So just let me write here, solution set will be all points on one side of this line. And the way you decide which side is to choose a test point. Pick a point that is not on the line. So for example, I can pick 4, negative 1. That's clearly not on the line, it's to the right and down below. So if I pick the point 4, negative 1, and let's take this and plug it into the equation of into the inequality. X minus 3y less than or equal to 4. When I plug this in, I have the inequality 4 minus 3 times a negative 1 is less than or equal to 4. And now I see if this is true or not. Well, the left-hand side here is 7. So the inequality says 7 is less than or equal to 4. That is obviously not true. And so the point 4, negative 1 is not on the correct side. And so really that does it. If this point is not on the correct side, then the correct side must be the other side. Just to illustrate, let's go ahead and be redundant and check another test point on the other side. So now I'm thinking about points above and to the left of the line, and notice that the origin is on that side. When I'm picking test points, if the line doesn't go through the origin, then the origin makes a good test point just because the algebra becomes so simple in that case. If I pick the test point 0, 0, then in my inequality it becomes 0 minus 3 times 0 less than or equal to 4. And notice because this is a linear equation, then all of the terms drop out and I don't even have to do the arithmetic. It's just saying 0 less than or equal to 4. That is true, and that tells me that 0, 0 is on the correct side. I already knew that from my other check, and so now the solution set is all of the points on the same side as 0, 0, in other words, up and to the left. And so what we would often do is shade that side of the line. All of the points in the shaded region satisfy this inequality. And because this is less than or equal to the points on the line, satisfy the inequality as well. Okay, that's something that you should be able to do. And finally, let's put those together and sketch a solution of simultaneous inequalities like this. Here are 4 inequalities. 2 of them look a little bit intimidating perhaps. The numbers are big at least, and then 2 of them are very, very simple. Well, let's go ahead and solve these. We'll graph the lines one at a time, and I'm going to speed up the process here a little bit because we've already done this. Regarding 15x plus 60y less than or equal to 4800, let's actually make that equal to, I'm going to graph this line first of all. And if I think about the intercepts here, when y is 0, x, the equation reads 15x equals 4800, and x is going to be 4800 divided by 15. So you can do this almost mentally. Set y equal to 0, this term drops out, take 4800 divided by 15 and get 320, comma 0. That's the x-intercept. For the y-intercept, set x equal to 0, this term goes out, and so the y-intercept is 4800 divided by 60. That happens to be 80. So here are 2 points on the first line. Before I choose where I put my coordinate axes and so on, let's find out what the other intercepts are, because I eventually want to graph all 4 lines on the same coordinate axis. So I want to be sure I can get the right intercepts, choose a scale that gets all of the intercepts graphed. I'm able to show all of the intercepts. The next line is 3x plus 6y equals 516. So set y equal to 0, and I get 3x equals 516. 516 divided by 3 is 172, so the intercept is 172, comma 0. And then set x equal to 0, and you get 6y equals 516, so y is 516 divided by 6, which is 86. The third equation is just x equals 0, and so this tells us that we're just dealing actually with the y-axis here. In particular, 0, 0 is both the x and the y-intercept. This line goes through the origin, as does the graph of the line y equals 0, which is the x-axis. So I want to be able to graph these 6 points, or actually 5 points, these 2 are the same, on one graph. I notice that all of the numbers involved are non-negative, so let's choose coordinate axes that allow me to use positive numbers for both x and y. I see my x's need to get as large as 300, so I'll choose about 1 square is 25 units or so, 25, 50, 75, 100, 75, 200, 2, 3, 4, 300. And then the y-coordinates will need to get as large as 86. How about we choose 1 square is 10 units. So here, for example, would be 20, 40, 60, 80, and 100. Okay. Let's go ahead and graph the lines one at a time. The first line goes through 320, 0. That's about here. Or maybe out just a little farther. .320, 0 is about right in here. And 0 80, of course, is right here. So first line is this one. That is 15x plus 60y equals 4,800. Second line goes through 172, 0. That's about right here. And also 086 is about right here. So the second line we're dealing with is this one. That's the line 3x plus 6y equal 516. The third line is x equals 0. That's just the y-axis rather. So x equals 0 is that line, and the fourth line is the line y equals 0, which is the x-axis. So that's this one. Okay, I graphed the 4 lines. Let's go back now and get the correct sides of each of these for the inequalities. So 15x plus 60y less than or equal to 4,800 is either all the points above and to the right of the red line or below and to the left. I'll pick a test point. Notice that 0, 0 is not on the red line, and so let's pick that. I plug in x equals 0 and y equals 0, and then on the left-hand side I'll get 0, then less than or equal to 4,800. That's true. And so that tells me that the origin 0, 0 is on the correct side of the red line, so I should shade everything below and to the left of the red line. I have 4 lines here though, and so I'm going to be shading 4 times, and the graph's going to get really messy if I do that. So how about instead of shading, we'll just indicate by arrows which is the correct side of the line to be on. These arrows show that I would shade to the left and below. Everything left and below of the red line is fair game. It satisfies the first inequality. Go on to the second one. 3x plus 6y less than or equal to 516. Again, pick the origin because it's not on the green line. And so I get 0 less than or equal to 516. That's true. So I also want to be left and below the green line. The third, x greater than or equal to 0. So that's either to the right or to the left of the purple line, lavender line, and you can just look at it, you know that positive x's are out to the right, and so we want to be on this side of the purple line, and y greater than or equal to 0 is on this side above the orange line. Okay, let's finish the problem. I want to find the points that satisfy all 4 of these inequalities. In other words, that's on the correct side of all 4 of these lines. So I look at this and say, what got shaded 4 times? And if you think about it, it's the region right in here. Be careful here at the upper corner. It's below the red line, right up here in the upper left-hand corner. Okay, there is a graph of the solution. One more thing. It's going to be very helpful in the application problems that we'll use this for to actually have the corner points of the solution region identified with their algebraic coordinates. So I look at this. This is a polygon. It's a region in the plane with straight line sides, and it has corner points as follows: here, and here, and here, and here. This is a polygon with 4 corner points. I'd like to know the coordinates of those corner points. Actually, I already know 3 of them. Here's the origin. That's clearly 0, 0. Out here, we already found the x-intercept of the green line. It was 172, and then the y-coordinate of that point, of course, is 0. The third point is here on the y-axis. We found that the y-intercept of the red line is the point 80, so this is the point 0, 80. And the fourth corner point is the intersection of the green line and the red line. Now, we haven't found that yet. How do you find the coordinates of the intersection point of a line? We just did that in the second example. So what you have to do is solve 2 equations simultaneously. Specifically, because it's the intersection of the red and the green lines, I'll use those 2 equations. 15x plus 60y equals 4800, and 3x plus 6y equals 516. So we want to solve those, and we want to solve them algebraically so that we can get an exact solution. I'm not going to work out all of the steps this time, but something to point out. If we call this equation 1 and this equation 2, I can reduce the size of the numbers involved. Let's divide equation 1 by the greatest common divisor of these numbers, which happens to be 15. And let's divide equation 2 by the greatest common divisor of the 3 numbers 3, 6, and 516, which happens to be 3. When I do that, I get the equations x plus 4y equals 320 and x plus 2y equals 172. That's not a necessary step, but it's a helpful one. It reduces the size of the numbers quite a bit, so as I'm doing the math, the algebra, it's easier. It's even easier if I'm using a calculator. It's easier to type a small number in than a big one. Okay, and then if I were to use the elimination method, actually the coordinates on the x's are both 1s, and so if I do a subtraction, if this is equation 3 and 4, if I subtract 4 from equation 3, I get 2y equals 148, and y turns out then to be 74. And then the last step, which I won't show, is to take the 74 and plug it back into one of the equations that have both x's and y's, perhaps right here, and then solve this equation and get x equals 24. So the coordinates of this corner point or intersection point are x equals 24 and y equals 74. Again, when we use the applications of this type of algebra, we're going to need to know the algebraic coordinates of the corner points of the solution set. This is going to be called the feasible region, the region that got shaded with all of the inequalities. Okay, again, if that algebra is uncomfortable for you, I suggest you find the PDF scan of some pages from an algebra book and look through those and refresh your memory of these algebraic solution techniques. If you're okay, if this seemed okay with you, then we'll be good to go in the next section with applying this to operations research problems. Thanks.